Hello, I'm Michele Fiorentino, professor at Polytechnic University of Bari, and together with Mine Dastan, we will present this paper called Gesture-Driven Augmented Collimator Widget for Precise 5 Degree of Freedom Dental Drill Tool Positioning in 3D Space. As we'll start with this presentation regards minimally invasive dental implantology. This is a growing market for medical procedure that replaces damaged or missing teeth with inserts. This technology has a lot of advantage, like reducing bone loss and surgical time and patient after operation. However, it's very challenging for the dentist. In fact, after the initial pre-surgery design, there is need of high special precision in a restricted oral cavity, with also moving tissues and low visibility. For this paper, our research addresses the problem on drilling the inserts. This is a 5 degree of freedom problem that uses commonly technology has two approach. One is hardware using surgical guides, and one is software by two-dimensional screen in operating theater. Both are not optimal because the hardware guides are expensive and takes time to produce, and they should be disposed, so not environment friendly. And 2D screen-based computer-assisted surgery requires divided attention and cognitive load to the doctor for mapping from 2D to 3D. So our research question is in this work was can we provide precise 5 degree of freedom visual guidance with augmented reality? There is a golden standard, and can we improve it? So we basically propose state of the art. We design a new augmented collimator widget, and we compare with the golden standard. Then we draw our conclusions. From the systematic review, we basically observed that there are in literature existing solution of augmented reality for this application. However, we noticed that most of the widgets available are quasi-static, and it provides only two-cylinder, very simple graphics, usually two cylinders that they should be overlapped by the user. And even in case of collimation, they provide a color change as only visual feedback. So we think that improve this design, and for that we draw inspiration from real life tools or material tools. One of these is the photographic cameras, the old-fashioned cameras with have split screen technology. Basically, you can reach very high level of focusing just collimating the vertical lines you have in your screen, and also engineering tools like the vernier caliper. These have and apart the collimation, it provides also amplification of the reading by enlarged scale. Those two tools together have something in common that's called Gestalt principle, discovered by German psychologists. Basically, one of these principles is reification. That means that our brain, human brain, can easily spot patterns in a pre-attentive, quick way. For this reason, we come up with many prototypes till this final one, which we find optimal. And it has 4 key features we see individually. The tool is not very simple to understand at the very beginning. The first is component separation. So we separate each of the error components. The error is the distance between the target in terms of position in space and the two angles that allow a very precise positioning that we need in drilling. And so separating each of these components in couples of collimation couples, which for each component, the couples provide collimation, and so quick preattentive shape recognition. In particular, we use triangles that collimates in an X symbol, and the semicircle, then when collimated, they create a circular, easy to recognize shape. So by component separation, added visual amplification. This visual amplification, starting from the accepted error, provides a linear gain, which allows to have a higher precision than visually available by increasing the visual error compared to the real error. This gain after a certain level, a certain error level, is not necessary, so we clamp it because it's not needed, as the user can see in the approaching phase where is the target. At the end, we arranged all the single collimators, the single components, in providing that our tool, we call it augmented collimator widget. This tool provides the arrangements, provide the maximum visibility in every tool position. And yes, for sure, in the first test, we noticed that in somehow during the collimation phase, the widget becomes a little bit crowded and overwhelming for the user. So we applied a dynamic hiding strategy. This make disappear the collimated widget in order to reduce the cognitive load from the user. So for the design of experiment,